So hello everyone, welcome you all at Lokesh Sir Unlimited Study Zone. So we're starting our chapter Physics, class 12th, Magnetism and Matter. So we have to study about the two different things here. First is magnetism and second is matter. So first question arises that what is magnetism? Magnetism is a effect. Nitin, magnetism is a effect surrounding the magnet. Okay. So when there is a magnet, or you can say current carrying conductor, either you have a magnet, then surrounding the magnet there is an invisible type of field that is called magnetic field. Okay, this magnetic field exists because of magnetic lines of forces. These are magnetic lines of forces originating from the north pole and continue to travel inside the magnet from south pole to north pole. It means they are forming a closed loop. So magnetism is the effect produced by the matter, produced by any magnetic uh, substance, or you can say a magnet. But second thing, the another part of this chapter is matter. For what matter we are studying here? So a matter is called magnetic material. A matter is called a magnetic material. Like you have a bar magnet, commonly known as north-south magnet. When you bring this magnet near a iron nail, it attracts the iron nail towards it. Sure. So this is a magnet and this one is iron. The material is iron. It's supposed to be a magnetic material. Fine. So guys, we have to discuss about the two things in this chapter. First is the cause. Okay. Who produce the magnetic power? That is magnet. And second, who realize the magnetic power? That is called magnetic material. So in two way we have to study this chapter. So first talk about the magnetism, a material that has both attractive and directive properties and attracts some elements such as iron, nickel, cobalt, etc. is called a magnet. Okay, so this is the first definition of magnet. What is a magnet? Magnet it itself a material that have both attractive as well as directive property. Attractive means it will attract magnetic materials. Okay, and directive property means when you suspend a magnet freely, then it will direct itself in north south direction. You are well known about this. Okay, when you keep a magnet freely suspended in a some space, some place, then it will direct itself, it will align itself in the direction of north and south. The property of attraction of a small bits of iron, sheet, cobalt, nickel, etc. towards the one uh, magnetite is called magnetism. Okay, so this property to attract these particle, okay, bits of iron, its steel and cobalt, nickel, etc. towards it, okay, is called magnetism. Now, there are many type of magnet. Out of them, first is natural magnet. Classification of magnet starts here. So very obvious, you know, a natural magnet is found inside the earth. Basically, it is the iron, ore of iron, ore of iron. So the chemical formula for the natural magnet is equals to Fe3O4. Fe3O4. Okay. So it is oxide compound of iron which attract small pieces of iron, cobalt, and nickel towards it. When suspended freely, comes to the rest along the north-south direction. Is it clear? Every line is clear to you now? Okay. Now talking about artificial magnet. Few magnets are found inside the earth. Okay, and they having attractive as well as directive properties. They are known as natural magnet. But artificially, we can produce or we can prepare some magnet by some special methods. Those magnets are called artificial magnet. Example, horseshoe magnet, a bar magnet, and a magnetic needle. All these type of magnet are artificially prepared. So these are called artificial magnet. Clear? Now talking about bar magnet. Bar magnet is very simple magnet. Okay, we use in our life also in physics lab. We have also seen bar magnet. A bar magnet consists of two equal and opposite non-separable magnetic poles. So there are two magnetic poles. One is north, another one is south. So the magnetic power for each the pole is same. For a given bar magnet or any type of magnet, there is a magnetic power that is called pole strength. Important line. This is called pole strength, and pole strength of the north pole is equals to pole strength of the south pole. Okay. So for both north and south pole, we consider a single letter for the pole strength, that is a small m. Understood, Nitin? So for the north and south pole, we will take a single letter that is called a small m. One pole is called as north pole and another is called a south pole. These poles are separated by a small distance. Yes. The small distance is called effective length. The small distance is called effective length. Remember, there are two type of length in a magnet. First, that is the end to end length in a magnet, that is called geometric length. So it is denoted by Lg. That is called geometric length. Clear? And inside the magnet, there are two poles. The poles are not exactly at the extreme of the bar magnet. Rather than they are somehow inside the magnet, somewhat inside the magnet. So the length between the poles is called effective length. So we have to only consider and encountered with a effective length. So two type of length are there. First is end to end length, that based upon the geometric length, geometric construction of the magnet, that is called geometrical length. And second one is the effective length. Effective length is the pole to pole distance. Understood, Nitin? Yes, Parth, Shom, sure, clear है? But they are not exactly at the end. For what we are talking about? We are talking about the poles. Poles are not exactly at the end of the bar magnet. The distance between two pole of a bar magnet is known as the magnetic length. Remember, the distance between two pole is called magnetic length, and the distance from end to end is called geometric length. Okay, the distance between two pole is called magnetic length. It is also called effective length. So Nitin, the distance between two poles is called magnetic length or effective length. Is it clear? Now see, the length between two poles is considered as 2L. For ease our calculation, we have to consider it 2 into a small l. Means there would be a center that is considered as O. Half of the length is L and another half of the length is also L. So we'll give a sum of 2L. Understood? So the total length between north and south pole is considered as 2L for ease of our calculation. Okay, now property of magnet. So property of magnet, when an ordinary bar magnet is dipped into the heap of iron fillings, the fillings, yeah, they, this, okay, it mean to say that when you dip some iron in an iron filling, then at the pole, most of the iron fillings are concentrated. Okay, means they concentrated at the place where the magnetic power is highest, where the attraction is highest, and these position are called poles. Okay, Yes, these preferred regions of attraction are called poles of the magnet. They cling to the ends of the magnet. These preferred regions of attraction are called pole of the magnet. So this is the definition for a pole of the magnet. A freely suspended magnet always stays in north-south direction. We know it very well. Unlike poles attract and like poles repel each other, a magnet induces magnetism in magnetic material. Yeah, this is a new thing. A magnet induces magnetism in magnetic material. How? Let us see. Like we have a magnet. This is a north pole of the magnet, and this is a south pole of the magnet. As you keep some substance, like this is a big big iron block near the magnet, then what will happen? Near the north pole of the magnet, there is the development of the south pole. Clear? In the iron piece, there is the development of the south pole, and the far end of the iron material, magnetic material, is magnetized as north pole. So, likewise, here the molecular magnet will established like this, north to south, and here again north to south. Okay. So, in a bulk way, this complete portion will rise to a give south pole, and this portion will rise to a north pole. So in this way, the magnetic material is magnetized. This is called magnetic material is magnetized. Okay. And this effect is only shown whenever the magnetic material is kept nearer the magnet. Yes. If you have a magnet, but the another magnetic material, north-south magnet is there, but the magnetic material is out of the reach of this field, like it is placed here. So you can see the lines of forces are not reachable for this magnetic material. Yes, understood, beta? Yeah. So you can see the lines of forces are not reachable to this magnet. So there is no generation of any type of pole there. So there is no type of any magnetization take place. Understood? So this will behave as a simple iron piece, not magnetized. So this line is very important. A magnet induces magnetism in magnetic material. Okay. Now this thing is going to be very important, that magnet induce magnetism, but there are different type of magnetism. So there is the induction of different type of magnetism in magnetic material. So on the basis of type of induction of magnetism, they are the magnetic materials are broadly classified into three types. Okay. One is called diamagnetic material. This is going to be very important classification. Diamagnetic material. Second one, paramagnetic material. And third one is ferromagnetic material. Okay, Nitin? So what I said, according to the property of magnetic material in presence of magnetic field. Okay. So in presence of magnetic field, there is induction of magnetism inside the magnetic material. Okay. And the magnetic material can show three types of effect, three types of different behavior. So accordingly, the magnetic material are classified into diamagnetic material, paramagnetic material, and ferromagnetic material. Okay. So later on, we will discuss about the type of magnetic material. Okay. An isolated magnetic pole does not exist. Yes. You cannot realize an isolated magnetic pole. Like if there is a north pole, then definitely there will be a south pole. Okay. Like this is a ring. If the left part from You see this ring from the left part, then the left part of the ring will be considered. If this is considered as North Pole, this means lines of forces originating from the North Pole, then definitely the another part will be as South Pole. Understood? It is difficult to draw this diagram because as our laptop screens are 2D, so can only imagine. So if the this pole from the left is north, then the another one will be a south. Yes. So you cannot separate a magnetic pole. You cannot realize a isolated magnetic pole. So isolated magnetic pole does not exist. It means where a north will exist, definitely there will be a south will exist. Okay. If you crush a bar magnet, if you crush a bar magnet and you will have 10,000 particle of this bar magnet. You make a powder of this bar magnet. Maybe in your childhood you have broken some bar magnet. Doesn't matter how many hammer you have beaten on it. If you got a single very thin slice of magnet, then it will have north as well as south. Understood? So means magnet is always exist in the form of dipole. You cannot realize a north pole. In the case of electricity, you can realize plus Q, you can realize minus Q. But in the case of magnetostatics, you cannot realize plus Q as plus plus north as alone. In electricity, you can realize plus Q as alone because isolated positive charge is possible, but isolated magnetic pole is not possible. When there is a north pole, it will it should have its south pole. Okay. So magnet is always exist in the form of dipole. Yeah, two poles are there. So such arrangement is called dipole. Okay. Any doubt till here? Nitin, any line that is problematic for you? Okay. So an isolated magnetic pole does not exist. Sixth, the two poles of a magnet are equal strength. Yes, just I said that if I have a magnet, one pole is north and another one is south. This pole is north and this pole is south. Then we have the two pole. The two poles can have only same pole strength. Okay. The effective power of both the poles will be equal. So means magnetic strength of north pole that is equals to magnetic strength of south pole. So both the pole strength are considered as M, but their nature is different. So some in some books you can see it's supposed to be north pole as plus M and south pole is considered as minus M. Okay. But by magnitude, numerically, their magnitude are same. They're having the same effective strength. So the two poles of the magnet are of equal strength. Now, talking to magnetic field. Now tell me, Nitin, what is magnetic field? Yes. What? No, no, no. You give. I want your answer. What do you think about magnetic field? Exactly. Yes. Reason around the magnet. You have a magnet, then definitely it can exert its effect up to a certain distance. Yes or no? Like this is a magnet. You can realize its effect up to a certain distance. The distance or the space up to where you can realize the effect of the magnet. What does mean this word effect? In physics, the word effect means interaction. Interaction means either there may be a force of attraction or it can be repulsion. Understood? Yes. So this is called collectively this term is called interaction. Means the reason the space around a magnet up to which the force on the magnetic material can be realized. Okay, okay? Yeah. So the space around a magnet within which it influence can be experienced or realized is known as its magnetic field. The line joining the two poles of the magnet is known as magnetic axis. So simple. Magnetic field lines, very important definition. Magnetic field lines. What are magnetic field lines? Yes, sure. Tell me, what are magnetic field lines? Magnetic field lines. Define magnetic field lines. Yeah, imaginary line. Exactly. But what type of imaginary line? No. Magnetic lines of forces are closed, smooth, okay? Closed curve, smooth curve, okay? Upon which a unit north pole can move freely. Yes, this is very important. Upon which, Nitin, is it clear? A unit north pole can move freely. Unit north pole can move freely. This is important. So here it is a unit north pole. So unit north pole means having the pole strength m north, having pole strength 1. So it can move freely. The trace out generated by this movement of unit north pole is called magnetic lines of forces. Clear? So these are closed continuous curve. Closed is smooth and continuous. Continuous means unbreakable. Okay. Yes. Outside the magnet, the direction of magnetic lines of forces are from north to south. And inside the magnet, the direction of magnetic lines of forces is from south to north. Okay. Understood? Nitin, is it clear? Yes. Now, second thing, what Shore saying is this is magnetic lines of forces. I am taking a typical illustration for this magnetic lines of forces. Then what does it mean? If you draw a tangent at any point on the magnetic lines of forces, sure, for what you're talking about, if you draw a tangent at any point of any point of magnetic lines of forces, then this tangent will show the direction of magnetic field at that point. Yes. So like if you draw tangent here, like at this point, so the tangent will show the direction of magnetic lines of forces at that point. Okay. Direction of magnetic field. Sorry. Clear, beta? Magnetic field. Oh, so it will show the direction of magnetic field. Okay, so the magnetic field lines of a magnet are closed continuously from south pole to north pole. It is talking inside the magnet. Yeah, inside the magnet is from south to north. But outside the body of the magnet, the direction of the magnetic lines of forces from north pole to the south pole means north to south. Clear? Second thing, third thing, at any point of the magnet, if you have drawn a tangent like this is the point. If you have drawn the tangent, then the tangent to the magnet at any given point, tangent to the magnetic field lines represent the direction of the net magnetic field at that point. Yes. So this tangent will show the direction of magnetic field at that point. Understood? No two magnetic field lines can intersect each other. Very obvious, very basic property. When two lines of magnetic lines of forces intersect each other, suppose these are the two different lines of forces. If they intersect at one point, then at the crossing point, there may be the two direction of magnetic field. One is this, denote to be B1, and another one is this, denote to B2. But A point cannot have two direction of magnetic field because direct magnetic field, magnetic lines of forces are the path traced out by movement of unit north pole. So if you place here a unit north pole, the unit north pole will be confused where I have to move, either in the direction of B2 or in the direction of B1. So practically, it is impossible that a particle can have, that a unit north pole can have two directions. Understood? So it is not possible that the two magnetic lines of forces may intersect. No, never. So all the things are clear up to here. Any problem? Sure, any doubt? Okay. Coulomb's law for the Coulomb's law of force for magnetic poles. This is first very important fundamental law, fundamental rule that govern the forces between two fundamental poles. So if you have two different poles of different pole strength, the first pole strength is given M1 and second pole strength is given M2. Okay? So if you have different pole strength, it means definitely there are two different type of magnets, because a single magnet cannot have two different pole strength. In a single magnet, there is a pole strength are always having the same magnitude. But if you have two different magnets, then it may be possible that there are two different pole strength. One is M1 and another one is M2. So the force acting between the magnetic poles, there is a force of either attraction or repulsion. Like if you have taken north and south, this one, so they will repel each other. Okay. But if you have taken north, this one, and south, this one, then these poles will attract each other. Okay. So the force acting, it is said to be force of interaction acting between the two magnetic poles, is directly proportional to product of their strength, and it is inversely proportional to the square of distance between their center. Means effective distance. This is called 2L. Okay. Huh. So what is the formula for Coulomb's law of force for magnetic force? That force is directly proportional to product of their pole strength, and force is inversely proportional to square of distance between them. So here the distance is d, so it is a square of d square, right? Give it equation number 1 and 2. Now if you collect these equation by 1 and 2, combining 1 and 2, you will have F is proportional to m1 m2 upon r square. Now if you eliminate the constant, then there will be sorry, if you eliminate the proportionality sign, what we have derived? Yet we have derived that F is proportional to product of pole strength, and this is equation number 1, and F is inversely proportional to distance chi square of the distance, inversely proportional to the square of distance between the pole. Now if you combine first and second, then F is proportional to m1 m2 upon d square, right? So eliminate the proportionality sign, then there will be a constant term always, m1 m2 upon d square. Here k is the constant of proportionality called magnetostatic constant. Yes, like there is electrostatic constant, here it is called magnetostatic constant, and this is equals to mu naught upon 4 pi, where it is applies in air or vacuum. In air or vacuum. Okay. So means when you provide the medium between the two poles, the intervening medium is air or vacuum, then there will be a constant acting, working as mu naught upon 4 pi. So place the value here. F equals to mu naught upon 4 pi m1 m2 upon d square. So this is the complete Coulomb's law. Okay. So this is the force acting between two magnetic poles, where M1 and M2 are the pole strength of two poles. So the value of K equals to mu naught upon 4 pi. Write the value of K. This is very important. It is mu naught upon 4 pi, that is equals to 10 to the power minus 7 Newton per ampere square. Then 10 to the power minus 7 Newton per ampere square. Okay, beta? Yes. Remember the direct dimension, sorry, the unit of pole strength. Unit of pole strength. So unit of pole strength is small m. Sure. Tell me the unit of pole strength. Yes, what? You have forget. Okay. So m, the unit of pole strength m is ampere meter. Okay. Ampere meter. Unit of pole strength is ampere meter. Clear? Mhm. Nitin, please write the Coulomb's law. Now, magnetic field strength at a point due to a magnetic dipole or a bar magnet. First, we talk about magnetic field strength. What is magnetic field strength? Magnetic field strength due to a bar magnet. So topic is magnetic field strength due to a bar magnet or magnetic dipole due to a bar magnet or magnetic dipole. Okay. So you just have seen that if there is a pole M1, this is the first pole M1, and up to a some distance R, suppose this is the distance R, there is some another test pole that is M naught. Okay. So this is first pole is small m. Consider is small m. So the name of this pole can be taken as source pole. Source pole, right? And m naught can be taken as test pole. Now, if they are kept at a distance r, then the amount of force acting on m naught, actually both will realize the same force, and the amount of force is given by F equals to m naught upon r square. Clear? Along with mu naught upon 4 pi. Sure. Is it clear? The force acting between the two poles here is equals to mu naught upon 4 pi m naught upon r square. Previously it was m1 m2 upon r square. So this is the force acting between the two uh, magnetic poles. This is given number 1. Now what you have realized, if m naught pole, that is a test pole, realizing the amount of force F, then what is the force realized by unit pole? So simple, by unitary method. If m naught pole realizing a amount of force F, then unit pole is realizing the force is F by m naught. Clear, Nitin? If m naught force is realizing a force F, then a unit pole will realize a force F by m naught. So calculate this one. So you can place 1 upon m naught, and the amount of force just we have calculated by Coulomb's formula, mu naught upon 4 pi into m naught by r square. They may cancel each other. So this is called force acting on a unit pole, and this is called B, magnetic field strength. So B equals to mu naught upon 4 pi into m upon r square. First formula, sorry, second formula for this chapter. So this is called magnetic field intensity or magnetic field strength. The strength of a magnetic field at any point is defined as the unit strength, the force experienced by the hypothetical North Pole. Yes, we have considered unit pole. Which one? Unit North Pole. So the force realized by unit North Pole due to any magnet is called magnetic field intensity or magnetic strength at that point. So very important formula. B is equals to force per unit North Pole. Okay, force applied by unit North Pole. If m naught pole, that is a test pole, it is realizing a force F, then unit pole will realizing a force F by m naught, and this amount of force realized by unit North Pole is called magnetic field strength at that point. So B equals to F by m naught. In vector form, B vector is given by F vector by m naught. Clear? Yes. So B equals to F by m. M is the pole strength of the hypothetical. M is the pole strength of hypothetical North Pole. That is, we have considered as test pole. Test pole. Clear? And we have this just derived this formula B equals to mu naught upon 4 pi small m upon r square. So very important, B equals to mu naught upon 4 pi small m by r square. Yes, uh, strength of magnetic field intensity or magnetic field strength, right? Now discussing about magnetic dipole. Yes, magnetic dipole is a arrangement, or you can say a magnetic dipole consists of two unlike poles. Unlike means equal in magnitude but different in nature. One having the south nature and another having the north. So the pole strength will be same but considered as negative sign. So here it is if the pole strength of south pole is m south, the north pole having the pole strength mn. So the magnitude of south pole strength will be numerically equal to the magnitude of north pole. Okay. So that's why we saying if we keep equal and opposite pole having the same pole strength very nearer to each other, or you can say they are separated by a very small distance, then this arrangement is called magnetic dipole. A magnetic dipole consists of two unlike poles of equal strength separated by a small distance. This small distance is called effective length or magnetic length. Okay. And just before I said that the length is considered as 2L, the 2L length is considered to make our calculation very easy. Okay. So this part of length are considered L and L will give a sum of 2L. Example, a bar magnet, a current loop, and all the solenoids are the example of magnetic dipole. Clear? So this arrangement, this configuration is called magnetic dipole, in which two equal and opposite pole strength, or you can say magnetic pole, are kept very near to each other. Then a very important quantity, physical quantity, is related to every magnetic dipole. That is called magnetic dipole moment. The strength of any magnetic dipole, like you have two magnetic dipole, first one is this and second one is this. You have two magnetic dipoles are there. Then the strength of magnetic dipoles, you have two dipoles. So the strength of magnetic dipoles are justified by a term that is called magnetic dipole moment. Magnetic dipole moment. Yes. Magnetic dipole moment quantify that whether the given dipole is strong enough. The magnet will have the high magnetic dipole moment will be considered as a strong magnet. So magnetic dipole moment is defined as magnetic dipole moment is indicated by capital M. Remember guys, it's small m is the notation for pole strength. Okay. And capital M is the notation for magnetic dipole moment. Magnetic dipole moment. A small m, a small m is the magnetic pole strength, that is a scalar quantity. And capital M is the magnetic dipole moment, is a vector quantity. Yes. Okay. So magnetic dipole moment capital M is defined as pole strength multiplied by effective length. Yes. So if you have a bar magnet or any magnetic dipole, okay, then its magnetic dipole moment is given by first pole strength. As both the poles are equal in magnitude, so you can select any of the pole strength m because both will give m and m, and the distance between these two poles. Okay, so the effective length will be considered as 12. And the direction of the magnetic dipole moment, very important, the direction of magnetic dipole moment, if this is north, this will is south. So the direction of the magnetic dipole moment is from south to north. South to north. Clear? So the direction of magnetic dipole moment is from south to north. Yes. So it is given by like this. Now here you have the magnet is just opposite that I have shown to you. So this will, here it is south, here it is north. So obviously the direction of the magnetic dipole moment is in the direction of its length. So this is 12. So magnetic dipole moment magnitude, this is equals to a small pole strength m into 12. But if you're talking about vector notation, so m vector equals to m multiplied by 12 vector. Because the magnetic dipole moment is oriented from south to north, and it will take the same vector in the direction of effective length. Clear? So capital M is equals to m into 12. Then now tell me the SI unit of magnetic dipole moment. What is the SI unit of magnetic dipole moment? Nitin, SI unit of magnetic dipole moment. Yes. Ampere meter square. Why? Why it is? See, the formula of magnetic dipole moment capital M equals to M into 2L, right? So the unit of M we have studied is ampere meter. Okay, multiplied. 2 is the constant that having no unit, but L is the length having the unit again meter. So it will produce the unit ampere meter square. Okay, so the unit of magnetic dipole moment is equals to ampere meter square. Now magnetic field at a point due to a bar magnet. Two important derivations are there. We have to calculate the magnetic field at a point due to a bar magnet. So suppose we have a bar magnet. So we have to calculate the magnetic field intensity or magnetic field strength at two situations. First, so this one is south, this one is north. So first, our first point is taken longitudinally in the direction of magnetic axis. This is the magnetic axis. So this point is point P is called axial position. So first you consider the point in axial position. Okay. And second, we have to calculate the magnetic field intensity just transversal on the transverse point. You can say transverse as perpendicular bisector, means both the distances are equal here. If this one is L, this is also L. Or you have to calculate the magnetic field strength intensity or magnetic strength at this point. This is called equatorial point. equatorial point. Clear? So in two places we have to find the magnetic field intensity. So yes, very important derivation. So first we are going to find when the point lies on axial line due to a bar magnet. So beta, once again, the when point lies on the axial line on the bar magnet. So here we have the point. This is the magnetic length 2L. So half of the length is L and another one is also L. And we have considered a point at a distance D from the center of the magnet. Remember, the point D is considered in length from the center of the magnet. Clear? Yes, Nitin, any problem? So we have two poles. One is south, another is north. And we have to find the magnetic field intensity here at this point. All we know, magnetic field intensity is the force acting on unit north pole. So we have considered here unit north pole. Now, first, because of south pole, and second, because of north pole. Now, look here. Magnetic flux density, or you can say magnetic flux density, in the place of flux density, you can write here magnetic strength. Just we have calculated magnetic field strength. So better to write here magnetic field strength. Magnetic field strength at P due to North Pole. So what is the formula? Yes, the formula for magnetic field intensity is mu naught upon 4 pi multiply by test pole upon distance square. Okay, square of the distance. So B equals to mu naught upon 4 pi into pole is M. Now tell me the distance here, beta. The distance here from this north pole to this point could be D minus L. Agree or not agree? As this distance is D, from center the distance is D, okay, and this distance is L. So on you subtracting L from D, this part will be remain as D minus L, right? So you can put here D minus L square. So this is first magnetic field intensity, and the magnetic field intensity is acting along N to P, means forward direction. Why? Because this is north pole and this is unit north. So north and north will repel each other. So this is B1 is acting towards the forward direction. Agree? Now second one, the south pole. You see the south pole having the distance from this point P as D plus L, L plus D. This point, the distance up to here is L, then it is completely D. So the total distance will be D plus L whole square. Okay? हाँ, Nitin, clear है? So this is the formula B2 is equals to mu naught upon 4 pi m upon dl d plus L whole square. So this is south pole. South pole will attract the unit north pole. So the direction will be towards the south pole, B1 and B2, right? Now, the net magnetic flux density, or you can say magnetic field strength. In the place of magnetic flux density, you can take the name magnetic field in strength. Field strength. So, beta, the magnetic field strength is given by B is equals to B1 minus B2. Okay, because B1 is going forward and B2 is going backward, and B2 is small because the distance from the pole, source pole, is very distant, very large enough distance is there from this pole south, and from north pole it is very closer. So the B1 will be high and B2 will be less. So the net intensity will be B1 minus B2, right? Now place the value of B1 and B2. So B1 is mu naught upon 4 pi into M divided by D minus L whole square minus B2 written as mu naught upon 4 pi into M divided by D plus L whole square. Now Take this one as a common, mu naught upon 4 pi m as a common. So remaining calculations are here, and you will finally get the formula B equals to mu naught upon 4 pi 2 small m small d, sorry, yes, you will get like this, mu naught upon 4 pi is small m into 2l into 2d d square minus l square whole square. Now small m into 2l is what? It is equals to magnetic dipole moment. So you can place here in the place of small m into 2l, you can place B equal to mu naught upon 4 pi capital M into 2d. So 2 can taken here, 2md upon d square minus l square ka whole square. A special case is there when the dipole is very small. So when the dipole is very small, this means if this dipole is very small enough, then this distance is L and this distance is D. So D is very larger than L. Okay, so you can neglect L in comparison to D. So you will have mu naught upon 4 pi 2 md divided by d square minus l square ka whole square. So it will be only d square minus L square is near about d square. Why? Because we have neglected L square. So here it will be d square whole power 2. So mu naught upon 4 pi into 2 md divided by d to the power 4. Now one power get cancelled out and it will be here d to the power 3. Right? So we have seen that intensity of magnetic field or magnetic field is strength in the position of equatorial is just half with respect to axial condition. Okay, so B axial is equal to just double of B equatorial. So question is, if any places at some distance from the center of the dipole, magnetic field intensity B is given 4 Tesla for equatorial condition, then the magnetic field intensity or magnetic field strength for the same distance in equatorial in axial condition will be 2 multiplied by 4 equals to 8 Tesla. Okay. For axial condition, it will be just double of the equatorial. I mean to say whenever B equatorial is given 4 Tesla and you have to find the B axial. So just make it double and you will have the B axial. Done.